In this video, we'll look at the length of a circular arc and the area of a circular sector. We've talked about angles in standard position, we've talked about coterminal angles, we know how to convert between degrees and radians, we know what a radian physically is. So now we'll use this information to find the length of a circular arc and the area of a circular sector. So as we begin to pursue a formula, an equation for the length of a circular arc, we should know what we're talking about when we say circular arc. So let's draw a circle. Here's a circle. Not a brilliant one, but it's something. And then let's say we have a radius of r and this angle theta. When we say circular arc, we mean this length here. We'll call that s. Now, to find an equation for s, we should consider the circumference of a circle. Now, to find an equation for s, we should consider the circumference of a circle, because we're looking at trying to find some fractional amount of the circumference of the circle. So the circumference c, we remember, is 2 pi r. So we have the circumference of the circle. Now, if we want an equation for s, we can kind of easily find it just by saying, all right, well, we have some theta radian out of 2 pi radians, and we're multiplying it by 2 pi r, right? So this is like the fractional amount we've gone around through our radians here. And then this would be the circumference of the circle. So you can think of it like this. We're taking a fractional amount and multiplying it by the circumference. So the 2 pi's will cancel out, and we're left with s equals theta times r. Typically, this is written r theta. So the length of a circular arc. In a circle of radius r, the length s of an arc that subtends an angle of theta radians is s equals r theta. And I've drawn an image here, a picture here, just so you can see, again, kind of visually what's happening when we talk about the length of a circular arc. Now consider the area of a circle. So thinking about the same kind of idea here, we can derive the area of a circular sector by saying A equals some fractional amount, right, theta over 2 pi, times the area of the circle, which we know that the area of a circle with radius r is pi r squared. So pi's cancel out, and we're left with 1/2 r squared theta. So again, just thinking about it as we're taking some fractional amount, we're taking a slice of the area of the circle, and that slice comes from theta over 2 pi. So the area of a circular sector. In a circle of radius r, the area A of a sector with a central angle of theta radians is A equals 1/2 r squared theta.